So our history is that both of us are not Bayesians, actually, and we don't really. We just use it as a computational device. So.
Don't tell any real patients.
Yeah. Okay. So I guess we will move on. So with the next topic, which is basically Bayesian EFA analysis. So if in version 7, you can actually do exploratory factor analysis with the Bayesian estimator. And you can do that with continuous and categorical variables. And we've actually been talking about Bayesian EFA for a long time. And we had different various ideas of how to do it. And now we've actually figured out the right way to do it. The description of the method is available in this paper, comparison of computational methods for high-dimensional item factor analysis that will come out on the website. With this implementation of Bayes EFA, this is asymptotically the same as the maximum likelihood estimation. One of the benefits of having a Bayesian EFA estimator is the fact that you can do EFA for categorical variables with a full information estimation. So we actually claim that Bayesian estimation is actually full information because the actual likelihood goes into the estimation. So, for example, one of the benefits of having a full information estimation is the fact that you can incorporate missing data in the best possible way. The traditional way of doing EFA in Mplus would be using weighted least square estimation. And with that estimator, you can get, for missing data, you can get pairwise deletion, which is a fairly good estimator, but it's not the best estimator. You can also do maximum likelihood EFA estimation. However, maximum likelihood with categorical data would use numerical integration. And the Bayes EFA estimator doesn't use numerical integration, and therefore it's feasible with any number of factors. So you can have 7, 8 factors. You can just estimate that with pretty much the same speed as, it's a fairly quick estimation. So another announcement for version 7 is that we've improved the ML estimator for EFA with categorical variables. That's the estimator that uses numerical integration. And in particular, for high-dimensional EFA models, you have to use Monte Carlo integration to estimate these models because otherwise the number of integration points grows exponentially. So pretty much, I don't think we've done with regular Cartesian integration. We have not done more than 4 or 5 factors. It will be pretty difficult even with the best computers out there. And so if you have a high-dimensional EFA model, then you have to use numerical. You have to use Monte Carlo integration if you'd like, if you want to go with the maximum likelihood estimation. So we've improved this estimation twofold. We've improved basically the starting values for that estimator, and now we basically use the weighted least square estimator as a pre-estimator to get starting values for the unrotated solution. That's one of the improvements. Actually, that solution is also used also for Bayes, so for the Bayes EFA estimation. And the second improvement for Monte Carlo integration in particular is a solution for the standard errors. Now, when you use Monte Carlo integration, very often there is a numerical imprecision goes into the estimation. And what used to happen in version 6 and before is that you get these saddle points as the solution. And when you get a saddle point, version 6 and prior would actually switch from the ML estimator to something called the MLF estimator. And the MLF estimator, when you get these kind of a complicated models, they, 40 binary indicators and say 7 or 8 factors, what the MLF estimator used to do is actually produce this higher, overestimates the standard error. So we've actually switched from that solution to a new solution that we found, which is basically how to deal with these saddle points issues, and basically we eliminate negative eigenvalues from the Fisher information matrix. Basically, that's the new solution for that we've implemented that for basically for the entire Mplus program. So let me just explain how the Bayes EFA works. And in the first step, we basically, in the Bayesian estimation, we estimate the unrotated model as a CFA model in using the MCMC estimation method. So the unrotated solution basically is a factor analysis model that has loadings fixed to 0 above the main diagonal and uncorrelated factors. So this is the unrotated solution. It is basically estimated as a CFA model, and you produce the posterior distribution using the MCMC method. And once you obtain the posterior distribution for this unrotated solution, to obtain the posterior distribution for the rotated parameters, we basically rotate within each MCMC iteration. We actually perform the oblique or orthogonal rotation, the optimal oblique or orthogonal rotation. So basically for each MCMC iteration, for each set of unrotated parameters, we actually do the rotation. We find the optimal rotated solution. And once you actually do this for every MCMC iteration, at the end, you actually get the posterior distribution for the rotated solution. So that way of doing Bayes EFA is actually the best way we could find, and that's it works very well. It basically it gives you the same results as maximum likelihood when maximum likelihood is computable. In this implementation in version 7, there is no priors. We did not implement any priors. With this algorithm, you cannot provide priors for the rotated solution. So it's easy for us to allow to specify priors for the unrotated solution, but that is not something that you can easily use because it's the unrotated solution. It's difficult to connect your prior information to actually the unrotated solution. So the current version will not have priors for the Bayesian EFA. And the other thing to understand about this Bayes EFA estimator is that because you have so many, in every MCMC iteration, you actually have to rotate the parameters. So basically, if you use 40,000, if the model actually converges in 40,000 iteration, which is not, that's a typical number of iterations. It could easily take that many iterations to converge. So then basically you have 40,000 rotation. Actually Mplus cuts the number of iterations in half, uses only the second half to estimate the posterior distribution. So essentially you still have 20,000 iterations to rotate. The good thing about the rotation algorithm is that it actually will use the parameter values are actually very close. They don't change that much from one iteration to another. So we have improved the rotation algorithm to actually use the values from the previous rotation. So the rotation algorithm is very fast. It's actually faster than what is being used with the ML estimator because of this sequential change. Nevertheless, you can, because there are 20,000 iterations, so you can still, there are a substantial number of rotations involved in this process. And one way to actually improve speed would be to use the thin command, which is basically with the thin command, you, instead of recording every iteration to produce posterior distributions, you can record only every 10th iteration or any kind of factor you would like. Setting the thin command, you can actually reduce the number of points in the posterior distribution and therefore reduce the number of rotations involved in the estimation. So the Bayes EFA estimation is essentially simple as that. You estimate the unrotated solution, then rotate all these unrotated parameter estimates optimally with different rotation metrics within each MCMC iteration. However, the main part of the Bayesian estimation is in this in the identification of the parameters. So the two separate identification issues that come up with the Bayesian EFA. You have identifications that are related to the unrotated solution, and a second set of problems is the identification of the rotated solution. So both of these problems are dealt with separately. With the unrotated solution, you have the identification. Both of these identification problems are very similar to label switching in mixture models, which there's plenty of literature on label switching in mixture models, but this is basically Bayes EFA. It doesn't exist. It's really coming out in version 7. This is the very first time anybody's ever talked about Bayesian EFA estimation. And so there's no really literature on these issues, but basically they're very similar to the label switching in mixture models. In the unrotated solutions, we only just the only identification issue is the signs of the loadings. If the problem here is really that when you are constructing this posterior distribution, you basically need to make sure that all the parameter estimates have no sign switches, because if you have sign switches, then you're going to end up constructing the posterior distributions from the wrong parameter estimates. And so, therefore, you have to actually make sure that you are resolving this label switching. And the label switching is very simple, actually, in terms of to understand it. Is basically that the posterior distribution of the parameter estimates has 2 to the power of m, where m is the number of parameters, symmetric components, and basically identifying the signs of the loadings is essentially carrying out one of these symmetric components to estimate to use one of these symmetric components to estimate the posterior distribution. Anyway, so the solution that we actually implemented in version 7 for the unrotated solution of the EFA estimation is also applicable to CFA models. So basically, we've, in version 6, we've worked with this Bayesian estimation of same models, and as the models actually got more complicated, we experienced a lot of non-convergences, and we didn't quite understand what was going on. But eventually, through this work and all other models, we realized that one of the problems was the label switching of the loadings. And so now we've implemented in version 7 this new algorithm that will automatically make sure that the sum of all loadings is positive, and that basically takes care of the potential sign switches of the loadings. And it will take care of also the unrotated solution for the EFA. So basically, as the MCMC iterations progress, in case you actually get this sum of the loadings to become negative, we flip the loadings. And that will resolve the sign switching problem. The second type of identification issue is the identification of the rotated parameters. Through the rotations, basically, the rotation doesn't identify the signs, and it doesn't identify the order of the factors. So there are 2 separate identification issues that occur that can mess up the posterior distribution during the after the rotation. So the solution that we've implemented to identify the order of the factors and the signs of the loadings is basically to minimize this sum of squares here. And basically, these are the loadings, the average loadings from the prior MCMC iterations, and these are the current MCMC iteration. So we basically minimize this sum of squares over all possible signs for these loadings and all possible permutations of the factors. So that's about 2 to the power of m times m factorial possible sign switches and permutations, and we basically minimize this. So we basically accumulate the average loading matrix across the MCMC iterations, and then we basically arrange the signs and the order of the factors in order to match that average loading matrix, and that will resolve the identification issues. We actually do this twice in the algorithm, once just the second time, just to make sure that there's no noise that has come from the averaging at the beginning. You have a question? Yeah. We don't do that. Let me just think for a second. We've actually never seen that problem with the bootstrapping stuff, but perhaps Well, do we actually do bootstrap standard errors for EFA? I guess we don't do bootstrap standard errors for EFA. So, I guess in complicated CFA models that could occur. So, but we have not implemented that for EFA. So, okay. Some of the other features that we have in base EFA is we have factor scores for the rotated factor scores also available. We get confidence intervals and the entire posterior distribution plots for the rotated factor solutions. And that's basically obtained by using this optimal rotation, which are different in every MCMC iteration. And we rotate the unrotated factors to obtain the posterior distribution for the rotated factors. We have these measures of fit with continuous variables. We have with continuous and categorical variables, we have this posterior predictive p-value, which is essentially similar to the standard p-value. And with continuous variables, we are in version 7. We've also come up with base factors, this is basically what the base factors do. In version 7, we've produced BIC now for all models with continuous variables. Just for single-level models, we produce BIC, and that BIC value can be used to estimate base factors. And base factors is basically an easy way to compare models. And the models can be nested or non-nested. You can just use a simple formula here to compute the probability, the odds for the two models to, the probability between two models to be the true model, basically. So if you have a base factor, and it's just an exponent of minus 0.5 times BIC, so you can basically use just a calculation by hand whenever you have two competing models. And you can use these big values that Mplus will produce. And if you, the standard practice is sort of that if the base factor is greater than 3, then you consider this as substantial evidence in support of H1 here. And you can reverse this 1 over 3, and then that will support H0. When we conduct EFA, we actually do this computation automatically. I'll just skip a few slides. Okay, let me just, here's a little quick simulation that we conducted to evaluate the performance of this base EFA estimator. So we have a EFA model with 7 factors and 35 ordered polynomous variables. And the model is pretty symmetric. It just have 5 indicators for each of these 7 factors. And basically what you have in the table here is the results for a main loading. Lambda 1 is a main loading that's, and this is a cross loading basically, which is 0. And you have these 5 different estimators here. So this is basically Mplus Monte Carlo. This is ML estimation with 500 integration points. And then you have ML estimation with 5,000 integration points. This is the new Mplus base EFA estimation, Mplus weighted least square. And also we've included this estimator from another program, which is called the IRT program. And it uses the Metropolis Hastings Robbins-Monroe algorithm. And the authors of the program actually published some articles to criticize Mplus methodology. And so that's why we included this program to compare to what they have. And here are the results, and you can see these are basically the biases are almost non-existent anywhere, and these are the coverage of the confidence intervals. And you can see basically that, first of all, the base EFA estimator seems to work the best of all 5 estimators, including Mplus Monte Carlo works a little with 5,000 points, works better than with 500. So we've actually, that's what we recommend now for Monte Carlo integration. But still base is slightly better in terms of coverage here. But from 500 to 5,000, the coverage actually improved quite a bit here. So integration with 5,000 is better. Weighted least squares is, of course, it's not a full information estimation, so it doesn't really take care of missing values that well. But it's performs very well here. And this is the results for this competing program. And you can see how low the coverage of the confidence intervals are. And here's basically another table that addresses the same problems. These are the standard errors. And you can see all the Mplus estimators produce pretty much the same value. And this computing program actually underestimates the standard errors by 60%. And this is, again, the ratio. Another way to evaluate the quality of your standard errors in a simulation study is to look at the ratio between the standard deviation of the parameter estimates across replications and the standard errors. And you can see that ratio has to be about 1. And this is what it is for the Mplus estimators. And again, you can see that the Bayes estimator here approaches 1 the best. And this other program has very poor standard error estimation. So, but the bottom line is that the Bayes CFA estimator is a very good quality estimator. So how do you do that? This is a simple example. It's based on example 4.1 from the user's guide, which is a simulated example. It has 12 binary indicators and 4 factors. And this is basically the standard part for doing EFA in Mplus. And all you need to do is just add this estimator equals Bayes to get the Bayes estimator. We are estimating EFA from with 1 through 5 factors. And this is what the new Bayes factor table looks like what you get in the output. Is basically, these are the posterior probabilities for one of these models to be correct. And in this case, you get that 99.559% with this kind of a probability. The true model has 4 factors, and that's, the number of factors is 4. However, there's a warning here, is that this actually is a power result, and we have to interpret it as a power result rather than as a complete truth statement. So what you have, the way you should interpret this result is that there's enough data to support a 4-factor EFA model, and there's not enough data to support a 5-factor EFA model. As a power statement, every statistical tool has different powers. So some other solution may have better power to identify, to extract more factors from the data. So you have to use it with a grain of salt here. The other thing that we've also identified is the fact that you have to use a substantial number of iterations if the sample size is small. So if the sample size is small, what happens is that the peak between the different EFA models are going to be close to each other, and therefore the actual decision about which factor model to use is going to need extra precision, and therefore you need to run enough iterations, Bayes iterations, to make that conclusion and to get that precision. And we have actually implemented in version 7 a new command, which is a way to specify a minimal number of MCMC iterations to be used in the estimation. And basically, that's the same as this bitter command actually is used to specify the maximum number of iterations. But if you put brackets around the number, then you actually get this to apply to specify the minimum number of iterations. And this is basically the summary output from the EFA model. You get the posterior predictive p-value, which is similar to the regular p-value. And the new stuff that you get also is this direct comparison between 4-factor model and a 3-factor model. And you can see this is the Bayes factor. And because it's 243, that means that the model with 4 factors is 243 times more likely than the model with 3 factors. And you get basically, this is the standard EFA output, and it's basically the same as the regular EFA output, and we've added these stars here to denote what loadings are significant. And in exactly the same way, as part of this Bayes EFA output, you actually will get standard errors and also confidence intervals that are not symmetric around the estimates. With that, I'm done with Bayes EFA, and we're going to talk now about Bayes factor score handling. So in the new version, we've improved the way factor scores are obtained with the Bayes estimator. In version 6 and before, you were supposed to ask to specify a data imputation command, and that's no longer needed. So we've actually used, now you can basically get factor score estimation simply by using the regular command, and that's the regular command. It's save data file, specify file, save factor scores, and basically what you have to do here is specify a number for the Bayes estimator, and this number is basically the number of points that you want to use to construct the posterior distribution. So the factor score basically comes as a posterior distribution, and the number of points in the posterior distribution is specified right there. We've also implemented this command factors equals, and basically if you want to obtain, if you don't specify this command, what you're going to get is just for each factor you're going to get mean, median, confidence interval, standard errors. If you want to get the entire distribution, you're going to get basically 300 points within each row. So the file can actually get pretty big, and that's why we implemented this command. And if your model has 50 latent variables and you have 300 points for each latent variable, that's going to be a huge file that no program will be able to handle, basically. So that's why we implemented this command, and you can actually specify which factors you want the posterior distribution to get, for which factors you want to get the posterior distribution. And you can use this posterior distribution also with the plot facilities in Mplus to get the actual plot of the posterior distribution. And what else do we have here? We also another advantage of the Bayesian factor scores is that it's more accurate than the maximum likelihood factor scores, especially in small sample sizes. The Bayesian factor scores are also more accurate if you want to use these factor scores in a secondary analysis, such as if you, for example, if you try to compute the correlation between factors. It's very well known that the maximum likelihood factor scores will underestimate the correlations between the factors if you try to use the factor scores to compute these correlations, but that does not occur with the Bayes factor scores. Another advantage of the Bayes factor scores is that it takes into account the variability of the parameter estimates. So maximum likelihood estimation, using factor scores from maximum likelihood, it takes the parameter estimates as fixed when it estimates the factor scores. But with the Bayesian estimator, you actually take into account the variability of the parameter estimates in your model. And another advantage is more practical is that with the Bayesian estimator, you actually get factor scores and standard errors for any model and any latent variable. That's not true for all ML models. So can I ask you guys a question? Have you ever run a model where you wanted standard errors for the factor scores and you couldn't get them from Mplus? Anybody? Okay, so we've improved version 7. We'll have somewhat more standard errors. We've improved the algorithm a little bit, so you get a little bit more. But again, it's not. We don't have. We cannot claim this with the ML estimators. We don't have standard errors for all factor scores. For every model, we actually give you factor scores. That's for sure there. But in certain cases, we don't produce standard errors. But those we chip off on that as well. So there are more standard errors now in version 7. And here's a little bit of a simulation to convince you that the Bayesian factor scores are more accurate than maximum likelihood factor scores. This is a simulated data, and this is in that paper that's on our website, plausible values for latent variables using Mplus. And we basically generate data from a factor analysis model with 3 indicators and 1 factor. We simulate data with small sample size, n equals 45 observations only. And because in this simulated data set we know the actual factor score values, we can compute things like mean squared error between the factor score estimates and the true value. And what you see here is the mean squared error for ML, and it's bigger than the mean squared error for Bayes. Also, what you see is the coverage of the confidence intervals for these factor scores, and for ML it came out as 20%, and for Bayes it's 89%. And also here's the average standard error, and you can compare that to the mean squared error. In principle, this should be very close, and they're close for base, and they're not close for ML. And what happens here is that one thing that you can try to remember is that the ML factor scores are particularly unreliable when the variances, the residual variances, that's not accurate here. That should say the residual variance of y is near 0. So when the residual variance of y is negative, sometimes the maximum likelihood to produce negative values, then that's called the Haywood case. And in that case, you cannot even compute factor scores. So that's yet another advantage for the Bayesian factor scores. But even if the value is actually positive, but it's near 0, and near 0 is not very clear what exactly it means, but if it's near 0, then the ML factor scores are particularly poor. And that's an example of that. So with that, I'm moving to another topic, which is some of these convergence issues that we wanted to address with the new version. So we've added some more convergence diagnostics with the Bayesian estimation. We've discussed a lot of this stuff in this rejoinder of the article that's coming out in Psychological Methods that Bengt mentioned. We've basically added, as part of Tech 8, we've added a test, Kolmogorov-Smirnov test, that basically compares the sample distributions between, the way Bayesian estimation works is you send two chains. You basically generate two chains. And what you do to determine convergence is you look at the posterior distributions for all the parameters between the two chains. And as soon as they align, they seem to become the same posterior distribution. You say that there's convergence. And the standard, the main convergence criteria in Mplus is called PSR, potential scale reduction criteria, that was invented by Rubin and other people. And it works, it works very well. We've experimented with, at least 10 convergence criteria before we actually went with that one. And this convergence criteria basically looks at the idea for that convergence criteria is basically puts the two chains, the posterior distributions from the two chains together, and it looks at the joint distribution and see if you can identify the two chains separately. As long as you cannot identify where the points came from, then you can conclude that basically the posterior distributions are the same. But that's not it's not a very rigorous test. It's a test that works almost always. But as these two pictures actually show you, this picture is a picture where it actually the potential scale reduction convergence criteria failed. So what happened here is so on a scale, basically the PSR is a value that's computed, and it basically, as soon as it gets down to 1, we claim that it's converging. And what happens here is you run the MCMC sequence, actually you hit the value of 1 sort of accidentally. And if you actually continue to run the MCMC sequence, what you want to see is that it never goes up above 1. But here it went back up. So with the Bayesian estimator, in any convergence criteria, there's a certain randomness in the estimation. So by accident, you can actually hit convergence with any convergence criteria. You sort of have to run the sequence longer and make sure that it doesn't, the convergence doesn't get broken. And that's an example where it got broken. So you run the sequence a little longer. If you actually leave it at M+, will stop here. But if you decide to run it longer, it's going to go back up, and that means that the actual convergence had not actually occurred all the way. So we've added this new diagnostics tool, which is the Kolmogorov-Smirnov test. And the Kolmogorov-Smirnov test is extremely strict. I mean, that's basically the strictest test that exists. It basically looks at the two separate distributions and rigorously tests whether they're the same. And that's not about testing whether the means are the same or the standard errors are the same. It tests the exact shape of the distribution. So it's an extremely rigorous test. Actually, here's another example. This is basically a non-identified model that we run. And here's what happened to the PSR. It concluded convergence right here. But if you run it longer, starts to look like it's non-identified model, but again by accident it went back down to 1. So twice Mplus would have actually concluded that it is convergent model. And if you run it long enough, you actually realize the model was not identified. So this new diagnostic tool comes out as part of the technical aid output. And it's basically a test statistic like that. It looks at the posterior distribution of from the two chains, and it looks at the difference and the maximal difference between for all values of the posterior distribution. And it basically we produce that statistics and also a p-value for that statistics. And as soon as if the p-value is less than 0.05, you conclude that there's no convergence quite. But again, in many cases, you are going to run into the problem of poor mixing, and that actually, so we've sort of we put a warning only when the p-value is greater than, is less than this value, 0.01, and but again, in certain more complex models, we tend to actually accept, decide that there's convergence as long as the p-value is greater than this number. So, but before I move on, I need to say this. So, people tend to talk about identification with Bayes the same way as they talk about identification with ML, and that's not right, because we have priors, and so certain models, as the BSEM methodology actually illustrates, certain models can actually be identified just from the priors. So, and if you want to read more about identification, convergences, and things like that rejoinder that is in the psychological methods, we've talked about these issues quite extensively there. So I won't go into that, but just keep in mind that identification of a model is not the same between ML and Bayes. And just because you have some kind of priors, and in most cases, in almost all cases, Mplus default priors, which you don't even need to look at, essentially, they are non-informative, and they will not identify the model. But in certain cases, just a model can be identified just from the prior, even though it's non-identified according to maximum likelihood. So here's just this small example of how to use Kolmogorov-Smirnov, and it's just a factor analysis model with where we have the mean of the factor is also free, and the means of the indicators are also free. So you basically have one more mean parameter than you can identify. And what after you run 1800 iterations, the PSR will incorrectly conclude that the model has converged. But if you look at Tech 8, and this is the end of Tech 8, and you can see that what are the p-values here? They are 0, and it actually these are the parameter numbers which you can find as part of Tech 1. And all these parameters are the mean parameters here, where all the parameters that you get p-value of 0 are the parameters that contributed to the non-identification of the model. So you can, so basically when you're not sure if a model is identified and you're not familiar with the model, you should run the sequence longer and look at that additional diagnostic tool that we've added. So basically in that particular example, if you actually specify a minimum, this is a new command that specifies a minimum of 20,000 iterations there, and you can run the model again, and then the PSR will actually conclude the same as the Kolmogorov-Smirnov criteria, namely that the model is not identified. And with that, I'm going to hand over the mic to Bengt. So let's try and switch the mics now. You want to put your...
Hey, can you hear me? Good. So how are you feeling? Anybody traveling from far away who's now starting to fall asleep? Where do you come from? Rotterdam, yes. Who's the person furthest away? Do we have anybody from another continent? Canada. Where? Canada, okay, right. Okay, well, welcome. So you didn't want to go to Johns Hopkins, you wanted to come to Europe instead?
Yes. I had a good excuse for it.
Say that again?
I had a good excuse to stop by your check.
Okay. Will you tell us later?
Yeah.
Okay. All right. So let me set myself up here. Slide 49 is such a nice slide, but we want to show it several times. And so Tihomir gave some of the technical underpinnings of BASE in the EFA setting, but also pointed to the more general issue of convergence. I think you want to have this picture etched on your retina because it's a very good story behind this. As Tihomir said, here you have the premature stoppage, automatic stoppage by Mplus. But if you continue, PSR goes away from the convergence close to 1, and only with a long chain can you finally, at this point probably, be sure that it's converged. And to remind you of that, we have a new output saying that wherever Mplus stopped, which might be here, it advises you to run the run with twice as many iterations as you had here. So twice as many is about here, where you can be more sure of the convergence. So you don't have to use the Kolmogorov-Smirnov approach, which is a little bit more involved, but you can actually stay with the PSR if you just treat it right and run a long enough chain. And it doesn't take that long to do it. So you shouldn't be afraid of using, say, 50,000 or even 100,000 iterations. That's all right. So Tihomir explained, talked about the first bullet, BASE EFA, so that's a new feature in version 7. I'm going to focus on BSEM CFA, B standing for Bayesian SEM. And we're going to learn that it's a very special kind of Bayesian SEM. It's not just vanilla SEM by the Bayes estimator, but it adds the idea of informative priors. So BSEM uses informative priors, whereas when we talk about Bayes as a computing algorithm replacing ML, we talk about Bayes using non-informative priors. Informative priors will add the analyst's empirical experiences in that substantive domain in a very intricate, interesting way. We're going to talk about bifactor analysis, which is an old technique that continues to be of great interest, and you will find references to several current articles in the psychological methods and psychometrica literature. And we're going to talk about a new technique, bifactor EFA, a new rotation technique. So you can actually do an EFA where you always have a general factor, which is the hallmark of the bifactor analysis. And we can connect that back to 1939, when Holzing and Swineford, somewhere in the Chicago area, did their classic study of mental abilities. We're going to talk about bifactor ESEM, ESEM standing for an exploratory factor analysis measurement model, an EFA measurement model, combined with a SEM general structural model. And we're going to talk about bifactor BSEM, which is the Bayesian version of that. So we have had two components so far. My very general, quick overview of things. Tihomir's more technical presentation of some technical underpinnings of the methods. And now we're going to go back to more applied. So it's going to go up and down here during the 2.5 days. Now you're going to see some real analyses done and we're going to think substantively a little bit. So we're going to be concerning ourselves with the Holzingen-Schweinfurt data, and you have the data. You will have them available to you. They're on the Mplus website. They were typed in painfully by my students in 1993, and they're still reeling from that, deep scars from that experience. No, it was actually divided up quite nicely. It wasn't too hard to do. And you will actually have a chance to experiment with those data in the last quarter of the day today, and try some of the analysis that we're going to describe now. And it's now about 11:30, and it's about midnight in LA, but we're still going strong. We want to use our time well, so we, as Ren said, we're going to cut into your lunch a little bit. I know you're getting hungry, but you know, this is hot stuff. So we're probably not going to finish until 12:15 and cut into your lunch. Anyway, this study from this little monograph, and actually you can find it at libraries. At least I found it at the UCLA library, and had it at home for a while. It was like reading a Bible there, a Bible of factor analysis, because these authors were forward-looking, very insightful, very advanced modeling thinking. Although what they did was what we would consider ad hoc estimation at this point, and I don't mean ad hoc in a derogatory way, but they did what they could with the estimation techniques they had back then, but their intention was exactly, well, I would say their intention was a BSIM analysis, but they just didn't have BSIM yet. So it's 26 tests optimally in the data set. We're going to use 19 of them at first, and then we're going to use 24 of them. And it comes from two different schools, which have a little bit different social background. And the data set actually can be used for multiple group analysis, not only the two schools, but you have two genders, and you have two grades. So 2 by 2 by 2, so you actually could do an 8-group analysis here if you like. So 19 of the tests were hypothesized to measure 4 mental abilities: spatial, verbal, speed, and memory. And that was based on a lot of prior pilot studies with tests that were well-known, well-developed. So this is a case where they do a study when the research area has come to a mature stage. They have a lot of prior knowledge about these tests. And they knew that these were going to measure 4 dimensions. In addition, as I said, there are 5 tests adding up to 24. 5 tests measuring mostly a general ability like deduction ability or a test-taking ability. Think general factor in bifactor language. So we're going to analyze 19 variables, and then we're going to analyze 24 later on. And we're going to work with fairly small samples, 145 and 156. So if the model doesn't fit, we cannot blame it on too large of a sample. Here is the 19 variable structure, the usual CFA picture with x's corresponding to free loadings to be estimated and zeros corresponding to a hypothesis. For instance, that for the visual subtest, verbal ability has no influence on visual, but spatial ability is the only ability that influences the visual subtest. So you have the subtest here in the boxes and the 4 factors corresponding to the 4 columns. So you can match it and look at it whichever way you want. So it's a typical confirmatory factor analysis pattern in the Carl Jureskog tradition since his 1969 Psychometrica paper. And these are strong hypotheses. These researchers really knew that you would expect large loadings here, and you would expect ignorable loadings where those zeros are. If you go to the 24 variable situation, you add these lowest 1, 2, 3, 4, 5 items, and they are only influenced by a general factor. General factor meaning that it's a factor that influences each and every item. And then the the 4 factors that we talked about before have now changed to become residual factors. So spatial, for instance, that factor explains correlations among the spatial items, correlations that cannot be explained by the general factor, but correlations that are over and above what can be explained by the general factor, so residual factor. So these are 4 now residual factors, so they're slightly different than the earlier factors. And exactly how, we're going to explain shortly. They're going to be uncorrelated with the general factor, all of them. Very often you see the specific factors also being uncorrelated among themselves, but we're going to be able to loosen up that restriction and make it a little bit more flexible and allow them to be correlated among themselves. So that's the playing field that we are working within. And here is once again the so-called BSIM paper that we referred to several times and will be out in a few weeks. And perfect timing with the new version 7. 2 commentaries by one group being Bud McCallum and others, and David Rinskop, and the rejoinder. The rejoinder took us a long time to do, write, and research as the original paper, actually. And this is what psychological methods does to you. But the results, I guess, is better than it otherwise would have been. So the key point here, folks, focus on this. Informative priors that are not identified in ML. Think about that for a while. Have you thought about it? Okay, you're done. How on earth can you identify parameters in base that are not identified in ML? What's the magic of statistics? No, but you bring in new information. You bring in information through the priors, information that you have from your pilot studies, from your empirical results in previous work. Haven't you always wanted to do that? Some will nod and some will say, no, that's terrible. I'm a frequentist. I only let the data speak. I don't want my prior notions to come in. Well, argument against that. Your prior notions should be and can be based on prior data, pilot studies. And they had many, many such studies. And you may say, well, I don't like it anyway. Well, then I'll tell you, if you've done CFA in the regular ML framework, which is the hallmark of SEM, with all those zeros, you are already a Bayesian. But you're a Bayesian that has used a little bit too strong priors. And that's what I'm saying in this slide. You have been over here insisting that the prior distribution for a certain loading, these are the loadings for the variables, the factors that are not supposed to influence the outcomes, the zero loadings, or cross loadings as we call them. Your prior is that everybody is here. This is what you believe, that there's a spike here. Whereas if you're Bayesian, you would say, yes, I believe that the distribution of this parameter lambda, the loading, has a mean of 0 and has a small variance around 0, but the variance is not exactly 0, which would mean this spike here. You have a little bit of wiggle room. You have wiggle room here, and the wiggle room can be given a substantive interpretation in the following way. You need wiggle room in life. So I'll tell you, if you're an item producer, I don't know how many of you actually write items, and there should be books on how to write items. I've searched for it, and they don't seem to exist very well developed. You know, here's a structure. Well, actually, let me take it to a simpler slide. If you are trying to write a visual item, and you should know that in Holzing and Swineford, each of these variables is actually a continuous score, which is a sum of many, many dichotomous items. So if you wanted to, you could go down on the item level, but those raw data don't exist anymore. And Holzing and Swineford, I bet, are no longer among us. So if you want to write a visual item, it is very hard to write it so that it's only influenced by your spatial ability and not by your verbal ability, not by your speed ability, not by your memory ability. It's very easy that you need a little bit more than your spatial ability, particularly speed, perhaps also memory. There will be cross-loadings, non-zero loadings out here. It's very hard to avoid it. They will be small, ignorable, but they could be statistically significant. So you need this little wiggle room, and here you have then a prior which has the mean of 0. We believe the essence is 0 on that distribution. But if you have a variance of 0.01, meaning a standard deviation of 0.1, multiply that by the usual 1.96, and you have 0.2 approximately, plus minus 0.2. So 95% of the distribution for that loading, you're saying, lies between minus 0.2 and plus 0.2. In a standardized metric, standard EFA, you would judge a loading of 0.2 and even below 0.3 as being ignorable. So here we're saying we have ignorable cross-loadings, but they're not exactly 0. So there, I moved you from being too strict of a Bayesian to a more reasonable Bayesian. And at the same time, I moved you away from being a frequentist to a Bayesian, I hope. So BSEM can be used to specify approximate zeros, not only for cross-loadings, as the picture on the right illustrates, but also for residual correlations, which we say are 0, right? We don't have any residual correlations among these short arrows here on the right. You can relax that if you want to. It's a little bit more complex than relaxing the cross-loadings. Third application area, direct effects from covariates. So think about a factor model like this, and then having predictors on the left, as in a mimic model. You have like gender, a grade, school type, other things. You're saying then typically in mimic that the covariates influence the factors but do not influence the items directly, but only indirectly through the factors. And in fact, you cannot identify both the effect of the covariates onto the factors and the covariates effect on the items directly. That would be a non-identified model. You identify some of the direct effects, but not all of them. But in Bayes, you can. You can. By having these kinds of priors for the direct effects, you can actually allow all of them to be free. It's very easy to do, actually. And then what comes out, you can see then which, just like for the cross-loadings, which parameters really are different from 0, significantly, statistically, and substantively. All of this has been available now for over a year in version 6. What has not been available is the last bullet. Group and time differences in intercepts and loadings. This has to do with measurement invariance. Measurement invariance across groups or across time is totally analogous. Think then about say a loading for two different groups. A loading that's a major loading, and you want it to be invariant across groups so that you know that you're measuring the same factor. Well, those two loadings for the two groups, now you're considering the difference between the two loadings. And you want the difference to have a small variance prior. You want the difference to have most of its mass at 0, but with a little wiggle room. So we're talking about 0 mean, small variance priors, in this case for the differences in measurement parameters across groups or across time points. That was not available in version 6, but it is available now in version 7. And I think it's really useful. I've used it quite a lot, and I like it. So, with that background, let's go to slide 64 and look at the 19 variables and do some analyses together. Let's first start with ML. So standard ML CFA up on the left. And here is ML for the two schools. And we have two types of analysis. We have the CFA, confirmatory factor analysis, and we have the EFA. And if you look at the CFA, the p-value, it's going to be the usual 0 for both of the schools. So this carefully constructed model on the right doesn't fit the data. by chi-squares overall test of model fit. And like we said, we cannot blame it on the sample size because these are quite moderate to small samples. So we will reject the model, and here we go for an endless series of model modifications that you have a hard time to rationalize to the reviewers. And we're going to hear more about how journals react to these analyses when Peg comes in and talks on Thursday. Okay, well, you can switch then and say, well, what about the EFA, the classic type of analysis? That has p-value that's healthy, you know, at least for the Grant-White school is really high. So, which says that we cannot really reject 4 factors, which was as hypothesized. It's just that we don't have as clean of a structure. Not even Holzing and Swineford could get that clean of a structure. But they were right about the number of factors. Well, if you do that, if you focus on the EFA for a while, you will see that EFA has 6 versus 9 significant cross-loadings, and that's shown on the next page here. So you have the, this is EFA solution. You have the bolded loadings here saying that that's where you have the major loadings, and they have the correct placement for both Grant-White on the left and Pasteur on the right. But you also have some cross-loadings. You have some, and like Tihomir said, we have the incredible innovation of adding asterisks. We just got tired of looking at the ratios in another table, so we just put it in here. How many significant cross-loadings do we have? 1, 2, 3, 4, 5, 6 cross-loadings here. And if you look at the right, I know the answer, it's 9. And it's particularly the spatial factor where you seem to have spatial ability seems to influence other items. So for instance, the straight item is supposed to draw on only speed ability, but it draws on spatial ability. And there are substantive reasons for that that we actually talked about in topic 1 of our 9-topic Johns Hopkins series. It's how the items are written. You have motivation for why you see cross-loadings. So, to summarize, we have cross-loadings fixed at 0. The model is rejected. And the model is rejected. You can do regular CFA by both ML and base. It's not only ML that rejects the pure CFA model. Base will also reject it. But if you use the more realistic hypothesis of small cross-loadings, which are not all identified in terms of ML, but they will be in base, you have this alternative of small variance priors. We already said that. And let's go to that. Let's go to BSEM of these 19 items. So what's the first thing that you see that's new here? Well, estimator equals base. But we're going to go straight into the interesting action here. We're not going to do the default base of non-informative priors. We're going to go into the informative priors. That's the means, zero mean small variance priors. Remind me to tell you about define standardize here, if I forget, but I don't want to do it right now. Okay, now you have the model statements here, and I'm going to move over here to show you how easy this is to deal with. So we're doing BSEM, and we're talking about the model, and we're going to say that the spatial factor is measured by visual cubes paper flags. That's these. So we're talking about these x's over here. And we do that for verbal, and for speed, and for memory. So far we're doing a regular CFA specification, except that we don't set the metric of the factor in the first loading. We set the metric of the factor by saying that their variances are 1. But that's trivial. The part here, cross-loading section, this section is what's new. So look at, for instance, spatial. Spatial by general through figure W. General is here. General through figure W. We're talking about these cross-loadings. And we don't want to set them exactly 0. But we are acknowledging that they are close to 0. We could give them a starting value of 0, like we do here. That is not at all essential. You don't have to give a starting value at all, in which case the default starting value is actually 1. But base quickly moves away from its initial values, as you can see if you look at the so-called trace plots. But we label, that's the most important part, we label these cross-loadings. If you look at the last one, again, memory by visual through straight. So we set visual through straight to close approximately 0. So we talk about these cross-loadings in the D1 through D13 labels. And then we say model priors, a very simple statement, A1 down to D13, all are distributed as normal with mean 0 and a small variance. And our favorite small variance is 0.01 for most cases, but not for all. That's your informative BSEM prior for the cross-loadings. Am I going too slowly for you? I'm not being facetious. You're an advanced group. So here, now you repeat what we had before, the ML analysis at the top of this table and the Bayesian analysis at the bottom. So once again, for Bayesian analysis, we can do the analysis for the Grant-White school and for the Pasteur school. And we can do CFA, as we started with the ML. And you see that also in Bayes, the CFA is rejected. We work with the so-called PPP, posterior predicted p-value. It's low for both schools. So once again, even with Bayes, do we reject the pure 0 cross-loading CFA. But here, CFA with cross-loadings, that's the BSEM line for each of the two schools. You can put BSEM out in the margin here. BSEM, and look, the p-values jump up. Now, the model fits the data because you've allowed a little bit of wiggle room here. Okay? And you can even do nice plots, which could be, impressing your friends and your editors when you send them off to publication. I'm not going to take time to discuss how to read these plots, but they look pretty. They're, colors and all comes out of Mplus. So now, here is the BSEM. Here are the BSEM solutions for the first Grant-White school and for Pasteur. And you have the same major loadings in bold where you expect them to be. But now, as it says at the bottom, now the number of significant cross-loadings have gone down from 6 to 2, 6 for the standard EFA for Grant-White, and gone down from 9 to 1 for Pasteur. So you have a significant cross-loading here, for instance, for Pasteur, but there are fewer of them. And you are able to stay with a simple structure. I'm going to summarize this in a while, but let me first do one thing. How big these cross-loadings are in the BSEM procedure is to some extent a function of the variances that you choose for the prior. We said 0.01. What happens if you chose 0.02 or 0.05 or 0.001? Well, here, and this is straight from the BSEM paper in Psych Methods, I've gone through this, and 95% limit has to do with what's the range of the values. And we said that for 0.01, it should say 0.20 here, I believe, 0.20 instead of 0.02. So that's the 0.2 plus minus 0.2 limit that we talked about. If you allow 0.02 prior variance, well, then you're saying that 95% of the loading distribution is between minus 0.28 and plus 0.28. And here it starts getting into, if you increase the variance of the prior further, you're getting into fairly major loadings, so you wouldn't want to do that. PPP is going to go up a little bit. You can actually gauge, as a gauge of which prior you should use, you could look at the fit. The fit is going to get better, a little bit better at least, if you allow more wiggle room. But the more wiggle room you allow, the more you move away from CFA and into EFA. But it doesn't matter that much here. And it doesn't matter in terms of the largest cross-loading. It doesn't matter as much either. The largest cross-loading is between 0.2 and 0.3 for any of these prior choices. And the factor correlations are also in a similar range. What this slide is essentially, if you just want a summary, what does this slide tell you? It tells you that the choice of prior variance is not important. The results are not dependent very much at all on your choice of a prior variance. And that's what you want. So you're recommended to, in analysis, in substantive analysis, if you can, do this kind of sensitivity analysis. The Bayesians propose, do a sensitivity analysis, an analysis of how sensitive your conclusions are to the choice of informative priors. You don't have to do a sensitivity analysis if you have the default non-informative priors, which you will probably use at least half of the time. But if you get into BSEM, and I know I'm repeating myself, but it's supposed to be a pedagogical repetition. If you get into BSEM, you are using informative priors. That's the feature of BSEM. And then you should add a sensitivity table like this. And in the paper, there's also one for the Pasteur School. So the choice of prior variance is not very important. What have we learned so far? Well, we reject the conventional frequentist CFA model, even for the classic data set of Holzinger and Swineford, even for a small sample size. And it doesn't matter if you use ML or Bayes, you reject CFA. Bayesian CFA with informative cross-loadings was not rejected. The Bayesian approach uses an intermediate hypothesis. It is less strict than a conventional CFA. It allows that wiggle room for the cross-loadings. But it is stricter than EFA. Because EFA is a little bit unsatisfactory, right? EFA says that there are 4 factors, but we know so much more about the items than that they measure 4 factors. We believe that the cross-loadings are very small, and EFA does not build that into analysis. So BSEM uses a hypothesis in between of EFA and CFA, allowing for cross-loadings, which are close to 0, and how close they can be to 0. I mean, you can put them at 0, but you can put them a little bit away from 0, is monitored by PPP. By that I mean, if you go from a very strict prior variance to a less strict, you have a better fit. If you made it even more strict, the PPP is going to crawl down towards 0. And when variance is 0, then you are at the CFA. So you should expect to get the CFA poor fit. So the PPP can be used together with the prior variances to gauge how close to 0 the prior information can be. Reverse way of looking at it, if you allow for very big wiggle room, there is a limit. If you allow for too big of a variance for the prior, you're going to get a non-identified model. And non-identification, as Tihomir showed, I think in slide 51, the PSR that bumped several times and then took off, going up, that is the hallmark of a non-identified model. The PSR value is shooting up and never coming down. And if you have too big of a prior variance, if it's too relaxed, then you're essentially saying if the variance is so big, it's non-informative. Then you're not adding that information that you need. Then you're back in the ML situation where the cross-loadings would not be identified. And the program will tell you so. So you can sit and experiment with that prior variance. Another thing about increasing the prior variance, before it gets not identified, the standard errors of the parameters of the cross-loadings would get bigger and bigger. More and more uncertainty. So it plays out in a very intuitive way. So now Bayes actually gives you modification indices in this sense, because modification indices are now parameter specific. For all the parameters that want to break out of their 0 state, they get estimated significantly differently from 0. So they are the ones that could be freed up. You don't have to stop here. You can free up the ones, the cross-loadings, the 1 or 2, in the BSEM solution that were significant. You can free them, and when you free them, other parameters get better estimated. So you can improve the estimation in that sense. It's very similar to ML modification indices. Final point, factor correlations. BSEM tends to be a compromise between EFA and CFA. What is the problem with CFA, and some of you are aware of this, I'm sure. Problem with CFA, with those exact zeros on your right screen, is that since you are specifying exact zero cross-loadings, you are forcing a lot of correlation between items from different factors. That correlation to go through the factors only, which means that the factor correlation will be inflated. When you have cross-loadings, more of the correlation between variables can get channeled through the cross-loadings. If you look at the covariance algebra, that's how it goes. A lot of zero loadings means that very much of the correlation between the variables goes through the factors, inflating the factor correlations. You don't want to inflate the factor correlations because that says your factors correlate much more than they actually do. EFA, on the other hand, may underestimate the factor correlations because you have too many cross-loadings. So too little of the correlation between the items or variables, observed variables, go through the factors. I think BSEM is a nice compromise between the two. And that idea has been picked up by, say, Herb Marsh, who's written a lot of, he got really excited and took off and wrote a lot of papers on it. And on our website you will see them mentioned. I'm not going to talk about target rotation, but just refer to it. It's a rotational scheme. A little bit similar in spirit to BSEM, but different and not as good, but you have that in the BSEM paper. I'm not going to talk about comparing BSEM and ESEM, but you can read about it also in the paper. I'm instead going to talk about bifactor modeling. It's pretty amazing how Holzing and Swineford conceived of bifactor analysis. Their hypothesis is clearly a bifactor model. By bifactor, I mean a general factor and then specific factors for certain types of items. They did the analysis by first getting rid of the general factor, and then they did regular EFA on the residual correlations after you got rid of that. And that's essentially what we do, except in a one-step procedure. So recently then, Robert Gibbons and Don Hedeker in Chicago wrote in Psychometric about full information item bifactor analysis, which is a big deal. When they say item factor analysis, they mean factor analysis with categorical indicators. And categorical indicators together with factors, which are continuous latent variables, that's that deadly combination. With maximum likelihood, when you have the combination of continuous latent and categorical observed, maximum likelihood requires an algorithm that uses numerical integration. You have integration going on, and numerically it's solved in a way that is quite heavy when you have many factors or many dimensions, as we will say equivalently. So it was a big deal when they talked about, when they say full information, that's a term for maximum likelihood in their case. Could be base, as Tihomir said, base is just as full information as maximum likelihood is. But they talked about maximum likelihood, and they pointed out that there were computational simplifications that could be done for the bifactor analysis, even though it looked like you have many, many dimensions, many factors. Algorithmically, it boiled down to fewer dimensions than you thought. And Tihomir is going to cover that. And Steve Reis at UCLA picked up on bifactor modeling also in a more applied paper, Quality of Life Research, for health outcome measures, and thought that was a good way to learn more about those measures. And then my successor at UCLA, Li Chai, he wrote a couple of papers in Psychometrica and Psychological Methods, where he also picked up on the Gibbons-Hedeker idea and illustrated how that could be done, how that could be utilized in various settings, and we will show you some of those settings. It becomes very useful in so-called testlet modeling, which is a popular way of writing test items, used, for instance, in PISA, and who knows what PISA stands for? Program in International Studies of Achievement. Well, nobody's here to contradict me, so Tihomir is going to talk about PISA analysis later. So the idea is that you have a, what's it called, STEM. That is, you have a story, for instance. The test-taking person is reading a story, and that story gives rise to a series of, say, 5 questions. Those 5 questions is what I understand as a testlet. That's like the spatial items in Holzing and Schweinfurt data. So those items correlate more than among themselves than they correlate with other items in the test that are not derived from the same stem, from the same story. So testlet modeling is a natural for this. So is longitudinal modeling, where you have the very standard across-time correlation for residuals of the same item at different time points, tend to correlate more than what can be explained by the factors. Now, we're going to focus, and Tihomir is going to get back to bifactor modeling in the item context. We're going to do bifactor modeling in the continuous outcome context. We're studying continuous outcomes here for a while. And we're going to talk about new methods that do not use regular ML-CFA. And we're probably not going to get through all of them before lunch, but some of them at least. We're going to talk about bifactor EFA, a new method that was developed, came out in last year and this year in Psychometrica by Bob Jenrick and Peter Bentler. And as far as I know, it doesn't exist in any other software. So but we put them right in. When they're good ideas, we put them in. And it's called rotation equals bi geomin. So you have this prefix bi combined with a traditional rotation. Geomin is a standard rotation, default rotation in Mplus. And we just add bi. And we're going to talk about bifactor ESEM, exploratory SEM, still with the same rotation. We're going to talk about bifactor ESEM with a general CFA factor. So ESEM can combine EFA factors and CFA factors. Not fully utilized yet. It's starting to catch on, but you can bring it further in your applications. And we're going to talk about bifactor BSEM. How are we doing on slide progression, Tihomir? Am I going too slowly? He thinks we're fine. When do you want me to stop? 20 minutes. In 20 minutes? Are we going to give them any chances to ask questions? He's thinking. So now, we have a new user's guide example. When it says UGX, that stands for user's guide example. And like I said earlier, there are about 22 new examples, to the dismay of Linda, who have to be able to fit it into her cover, which is, may not have a thick enough back. But this is a simple example of bifactor. So you have the usual type equals EFA. You go from 2 to 3 factors, but now we have the new rotation. And the number of factors, 2 here, is the general plus the specific factors. So when you say 2, we only get 1 specific factor. If you say 3, we get 2 specific factors. So it's the general plus the specific. That was easy, right? Now you can do this in an ESEM framework. And for those of you who are not familiar with ESEM, the hallmark, the signature of ESEM is that you have this little concoction, the parenthesis asterisk 1. You can vary it a little bit, and so you actually use bi here. So in the middle of an EFA, you actually use the bi statement, which usually belongs with CFA. So you say you have a factor that's general, and then 2 specific factors, F1 and F2, and they're measured by Y1 through Y10. We don't say which items measure which factor. We let the program tell us, and we want to do that in a in an EFA ESEM type of fashion, and we specify rotation equals bi geomin. This way of doing the analysis gives exactly the same result as in the previous slide. 4.7 and 5.29 give exactly the same results, except that ESEM produces things in a raw metric, so not in a correlation metric, but in a covariance metric. So when you use ESEM, if you want it in a more EFA-like correlation metrics, you ask for standardization with respect to the factors and the outcomes. And then you will see exactly the same numerical values for the two. Now what about bifactor ESEM? What is that? Well, you have a CFA statement in the midst of it, a general factor measured by all of the 10 items, setting the metric in the factor variance. And then you have the specific factors measured by 8 of the 10 items, just like the Holzingen-Schweinfurt 24-variable example. So those 8 variables are subjected to ESEM, that's the ESEM hallmark, with a regular rotation, not a bifactor rotation, because we already have a general factor defined in CFA fashion. So we do a regular geomean rotation for, with respect to 2 factors measuring, or 2 factors measured by 8 of the 10 items. And then we say that that general factor is uncorrelated with the specific factors. That's a new ESEM type of analysis. And then BSEM, and you can try all of these variations this afternoon. You can do it on Holzingen-Schweinfurt, or I don't know if you have any other data. So you have then, now it's BSEM. So you have to keep this, you have to keep EFA separate from CFA separate from ESEM separate from BSEM. It's a problem of excesses here. Estimator's base, we read this. This is a CFA type of factor. And then we have a CFA factor. This is how you read this. F1 is measured by Y1 through Y4. And you might scribble out here. Scribble to keep you awake. Major loadings is what you should say here. Major loadings. And then measured also by the other items. But you can write out here minor loadings or cross loadings. We give these F1 cross lambda loading 5 through 10. We give them labels. These are the ones that we expect to be small. So these are the small minor cross loadings. Likewise for factor 2, major loadings Y5 through Y8, minor loadings given labels. So you write minor cross loading here, close to 0. And the specific factors are uncorrelated with the general. And now we work with these labels for the cross loadings in the model prior statements. So those cross loadings, all of them, fx lam 5 through f2x lam 6, are given a prior, an informative prior with mean 0, and prior, small variance prior of 0.01. You didn't remind me, folks. Yeah, right. Lots of help I get here. If you go back to slide 68, one important point here. Slide 68. Look at the defined statement. These prior variances, the choice of prior variance is related to the scale of the variables. How big of a loading is related to the scale, the variance, say, of the observed indicator. So if you say prior variance 0.01 and some variables have variance 100 and some variables have variance 1, that prior is not going to have the same effect. So you want them to have the same effect. And these Holzingen-Schweinfurt variables have very different variances because some of the variables are sums of only 10 or 20 items and some are sums of 50 items. So they have different variances. So you can't, what I did here was to standardize, so all of the variables have variance 1. That is not innocuous, which is another way of saying that could be dangerous. That is, there are some models that are not scale-free. EFA, this kind of model is scale-free. In scale-free models, this is okay. A not scale-free model, as an example, is a growth model. A growth model where you really want to study the variances changing across time. If you standardize, you've lost information. Likewise, any model that holds an equality of loading, say, across items is not scale-free. But for scale-free models, you can standardize. For non-scale-free models, you could do the innocuous approach of, say, dividing variables with very high variance, divide them by 10 or 100, something that's not sample dependent, a constant, is typically okay. So which slide were we on? 80? So we were here, right? So remember that caveat. Choice of prior variance is directly related to the scale of the variable and has different effects for different scales. Another topic, another influence on prior choices that we are less knowledgeable about, and we hope you can help us study, is how prior variances should be chosen in relation to sample size. Sample size of 100 is quite different from a sample size of 50,000. And the prior, prior has one piece of information, the data has another piece of information. If you have a lot of data, it will overwhelm the prior. So maybe with a larger sample size, you have to have a prior with smaller variance. We don't quite know yet how that works, but we're thinking about it. You're thinking about it right now, right? So now we switch to the bifactor case, and you can tell because you have a general factor, and you have x's all the way through in the first column. So we're in the bifactor realm, and we do bifactor EFA, and we do it by bigeomin here. This is now applied, not user's guide examples, which is always for simulated data. This is for real data. And we only work with 5 factors here because 5 factors mean 1 general and 4 specifics. And that's our hypothesis, so to speak. Here's the bifactor EFA. Rotation. We don't do anything. We just rotate our way through here. Looks pretty clean, right? These are half of the variables on this slide and the other half on the other. We have some significant cross-loadings here. Here's the rest of them. We actually have 6 significant cross-loadings. This is for Grant White. That's pretty much like the EFA for the 19 variables, but now we have it for the 24 variables in the bifactor model. So this is not BSEM. This is bifactor EFA. Now, are we doing ML or are we doing Bayes, folks? And the answer here is bifactor you can do in Bayes and ML, but here, since I didn't mention the estimator, the default estimator is ML. So we're in ML land. We're going to jump back and forth. We're just trying to keep you awake, even people from Canada. I saw you nodding off there. That's okay. Okay, and you get factor correlations. Look, we have factor correlations in the bifactor EFA, and they're significant, which may indicate actually that you need another general factor. There is a researcher in Sweden, Jan-Erik Gustafsson, Gothenburg, who's done extensive modeling of the bifactor kind. He likes that very much, contrasting that with second-order factor analysis modeling, which is slightly different. And he argues that there is information to gain here in learning which specific factors correlate, as I said, may indicate a need for other general factors. How to understand these, you can read, and how to understand the rotation, you can read about the technical details in those 2 Psychometrica articles. And it's quite an interesting story. Bob Jendrick is pretty clever when it comes to rotational matters. He's written many Psychometric articles on it. Here we are in Altingen-Schweinfurt data, and we do bifactor ESEM, which again you recognize by the ESEM hallmark here. And it is actually in combination with the general factor. So we have CFA combined with EFA for the specific factors, specific S1 through S4. Of course, the usual spatial, visual, memory, speed type of thing. And bifactor ESEM, here you have them, a clean structure once again. And look, it's empty here, and it's not a typo. But the bifactor ESEM did not include any cross-loadings for the last 4 items. And I would argue that there is an advantage to having some items in your test that only influence the general factor. Sorry, that are only influenced by the general factor. Some items that are only influenced by the general factor, because that tends to define the general factor better. So 6 significant cross-loadings here for ESIM. Still pretty much like EFA. Now let's go to bifactor BSIM. And I think we'll stop after that. We have BSIM here, which means that we're going to have cross-loadings defined. And here you have it. For the spatial factor, these are the major loadings here. If you match that with a figure, path diagram, you can see why. And here are the cross-loadings. Continuing on to the next slide. Anything that's labeled is cross-loading. Go all the way through here. And then you have the model priors, zero mean, small variance priors for the cross-loadings. And you would ask for STDY standardization. And here you have the clean structure. We see one significant thing here, 2 for spatial, but only one more here. So all in all, 3 significant cross-loadings, all for the spatial factor. That's down from 6 before, so we have a cleaner structure here by far. And here's the summary, folks. For the Holzinger-Schweinfurt data, bifactor for the 24 variables now, before we told the story about 19 variables, but here's the 24, which is the full story. There are actually 26 items, but 2 of them were just revisions or replacements. The full story is really for the 24. Bifactor CFA does not fit with ML or with EF base. EFA with bifactor rotation, it fits well, just like EFA did, but you have quite a few significant cross-loadings. Holzinger-Schweinfurt may not be happy with that. Bifactor ESIM, where we specify a general factor, and do regular rotation, where we allow the last 5 items to only be influenced by the general factor. Still not a clean structure, only a clean structure when we turn to bifactor BSIM. No rotation. Because we handle sort of the rotation by the priors on the cross-loadings, only 3 significant cross-loadings. We discussed that in the rejoinder to the BSIM paper and claim that this kind of bifactor analysis outperforms all other bifactor or other factor analysis I've ever seen of the classic Holzinger-Schweinfurt data. So finally, I think we have a method that they would have liked, but they can't argue, so I shouldn't say that, I guess. And with that, folks, I think we should probably take some questions and answers before we switch over to 2-tier, not to exhaust you totally, because we want to be back here by 1 o'clock. Is it 1:30? 1:30. Yeah, that's right. So who has energy to ask questions? Richard. Do you want a microphone? Slide what? Slide 47. In this case, it's two-tailed, right?
Basically, the significance is judged only on the confidence interval. So it's not, it's a credibility interval, the metric credibility interval that has 2.5% on the left and 2.5% on the right. So it's not really based on a p-value, it's based on the confidence interval, which in base is,
So you have the base confidence interval is called a credibility interval, and if that interval does not cover 0, if the interval does not cover 0, you will get an asterisk, then it's significant. So in that sense, if you're a frequentist, it is a two-tailed affair. Okay, more questions? Yes?
What would you think about a similar approach to if you think, for instance, path model, where you also say, where theoretically you assume a certain pattern of effects fixed to 0, just like in a
So the question is, what if you consider path modeling instead, and you have major hypotheses of 0 paths, but there could be the counterpart to cross-loadings. And actually, that came up in the discussion of the BSEM paper. David Rinskop, in a commentary, commented on that. What about major loadings and in the structural part? And we added an example on that Kaplan model that you saw initially with the diagrammer. The same thing could be done there, not only for small loadings, as that example shows in the paper, but you can also have a prior for major loadings. That is, you can say that the major loading, you expect it to be, say, a mean away from 0, like around 1. And that can actually guide the analysis, as that example shows quite well. So, yeah. Yeah. More questions? Yes?
If I continue the major loadings, and we know that some measures have, let's say, between 55 and 65, some have between 70 and 80 on the loading of the factor. So what is the best practice regarding the prior for the major loadings themselves?
Okay, so in all of these analyses, the prior for the major loadings was non-informative. And I'm glad you asked. This is so great, the Q&A session. The major loadings were not giving any priors. We said nothing. In Mplus, then that's the same thing as saying that the prior has a normal distribution with mean 0, which seems scary when you think it's a major loading, but with variance 1,000. So you're saying nothing about it. You let the data totally inform about that major loading. Now, you could modify that and have some kind of informative loading prior for the major loadings as well, but typically you wouldn't. More questions? Yes, in the back. So the question is, in ML we're used to worry about standardizing variables in the analysis. So that's what I wanted to point out, that it has to be a scale-free model. The same problem exists in Bayes. So EFA is a scale-free model, and therefore it doesn't hurt if you standardize. But like I said, a growth model is not scale-free, so their Bayes as well as ML would be hurt if I standardize. So in that case, if you want to change the scale, do it by a constant of dividing by 10 or 100. It's a better approach. Yes, Jason. Why would you use priors for major loadings? That's a good question. For path loadings? Yeah, well, yeah, exactly. And if you read that paper, that is what's on your reading list. That last example that was added, I guess added in the rejoinder. Well, I see. The rejoinder we didn't give you. So you have to go. Actually, we don't have it posted either. So if you send us an email, we'll send you the rejoinder. And in the rejoinder is a special section on the Kaplan model analysis, where major loadings are given informative priors, because it was a case where in the Kaplan model, influence from, we talked about direct effects from covariates to indicators, but here's a case of direct effects from indicators to another factor or to another outcome. And there were more, the direct effects could actually overtake the major effect from the factor unless you gave the factor a major structural path informative prior. Now, that may sound like gibberish, and probably is, but that rejoinder will explain in the Kaplan analysis why you might want to do that. Because if your theory and prior data says that there should be a major influence there, why not use that? Now, that brings me to another caveat. I worry that Bayes in Mplus is going to be misused. I worry, for instance, that a person has a mediation model and puts a prior on one of the mediation paths, the A or the B path. A prior is chosen so that the indirect effect, the product, is significant. Because they believe it's going to be significant. So they impose priors till they get what they want. Don't do that. Don't base the priors on your own opinion if that opinion is not informed by data and previous analysis.
Actually, yes, sir. So that would be really hard to do if you have a lot of data, because your priors, you have to really push the priors really hard to actually get your stuff. I mean, the main thing is like your priors don't really matter with base if you have sample size of 100 or more. So now that's documented that I said that. But,
Yeah.
yeah, you can't abuse the priors really that much. You have to, the data will speak for itself. So.
But the reason I mention it is I've already seen it in practice for somebody who had a small sample size and played a little too fast and loose with, I won't mention any names, fast and loose with the priors. And I worry that it could be abused that way. But I'm sure that journal editors will help stop that. We'll stop here and give you lunch and get back to your question later.